Good evening all of you. In the last class we had completed two exercises. One is the implementation of the convolution layer along with the forward and backward propagations, right? We have done it successful assignment 8. In the assignment 9 is the implementation of max pooling layer along with the forward and backward operations. Done it? Remember? These two exercises need to be finished within the first 30 minutes. After 30-40 minutes, I am going to release the last one which is related to this implementation of CNN. By releasing the last exercise, all of you need to complete all the prior exercises. You have 30 to 40 minutes of time you are going to get. Fine. Let me check. Anybody is there struggling with the max pooling layer or convolution layer implementation? Okay, just have a look on this one. We will do it parallelly. No, don't worry, we will do it parallelly. Just look at the slide. Remember, please try to recollect. Our task is building and training a simple convolution neural network. We have to construct and train also on a sample data set. We reached to the stage of step 3. First 3 steps were completed. Right? Now we need to move on to the remaining steps. Look at the 4th step. What is that? Implementation of a loss function. So for our case, a scenario of the simple CNN which we are going to build, we are considering the task of classification of images, labeling the images. So binary cross entropy loss is a suitable loss function. So the next step is we need to define the forward and backward operations of the binary cross entropy loss. That's the first step, right? This part already you have executed in the DL sessions itself. Do you remember? You have seen the definition also. You had implemented and executed by yourself during the sessions, DL sessions in the first 2 weeks. Anyhow, the instructions are provided. That's the first thing. Next, second is, look at the next step, implementation of the dense layer, fully connected layer. This also you had implemented in the beginning sessions. Do you remember? Simple convolution, a simple dense layer with the input and a number of hidden nodes. Right? That is the next step. How the forward and backward with the initialization of the weights and the biases, how the forward propagation will go on and what happens with the backward propagation. So dense layer implementation is the 5th step. Next is the activation layer. We have a very good number of activation layers. As I am repeating, this is a simple convolution neural network we are building. We are restricted to, confined to only one simple activation function, sigmoid. So the next step in the 6th step, you have to implement the sigmoid activation layer with forward and backward operations. And another one is reshape layer. What is the need of reshape layer? Do you remember? In case of convolution neural network, you can find the image, somewhere it is. So max pooling, yes, yeah. I am just showing that image again. Once you completed the stages of the convolution followed by the optional pooling operations, you will get the image dimensions of multi dimensions. At the last stage, once all this pooling and downsampling, the convolution and the downsampling is over, the next step is we need to pass these input features which are extracted from the convolution layers to the dense layer for further processing. Right? So dense layers is of one-dimensional input taking. So these multi-dimensional data which is output of this feature maps is to be converted flattened and mapping to the dense layer dimensions. So there you need to reshape the dimensions, nothing but the output of this convolution layers to match with the dense layer. There we need of the reshaping of the dimensions of the data. So reshape layer is the another thing, that is the next step which is to be implemented. Okay? Right. Thus all these steps to be done. So coming to the concept of step number 4, 5, 6 and 7, all these are the simple classes are already done part. With the instructions, I designed one exercise with all these 4 steps included in a single one that I am going to launch now. You need to do this one. This is assignment 10, already we have done until 8 and 9. Now the assignment 10 I am going to launch. and released successfully. Some of you please confirm whether you are able to fetch it or not. Assignment 11. Can anyone confirm? Sorry, not 11. CNN 10. Right. So, in this assignment you have 4 parts, 10A, B, C and D. You can see the first one, 10A, which is the implementation of binary cross entropy loss and its derivative, which resembling the step 5, right? Binary cross entropy loss and its derivative is to be defined. So, you are going to define 2 functions, one is the binary cross entropy loss and the second is it and its derivative. 2 things we need. The instructions were given clearly and you know the definition of the binary cross entropy loss. With the actual and predicted values, we will calculate the difference between this actual and predicted in terms of different formulas. Here we are using binary cross entropy loss function. The formula for the binary cross entropy loss calculation is well known to you. You are all well aware of, I hope. Not hoping, you have done it in the very beginning sessions. I am sure about it. So, compute the loss using the given equation, and in order to implement that logic also, the required torch functions are also provided in the instructions. Log function and mean function from the torch library. With the help of these 2 things, you are supposed to perform this operation. Thus, formula you need to implement. So that you can define the binary cross entropy for the given y true and y prediction. Both the true and predicted values of the output parameter y, this binary cross entropy loss is to be calculated using the same formula. So that has to be written by this function. It's a so simple implementation. And coming to the another definition, that is binary cross entropy derivative. During the back propagation, the loss derivative is to be calculated at the very beginning. Once the forward pass of the network is completed, first step is you need to calculate the derivative of the loss that you are getting. So the loss which we had used and defined is the BCE. So for the same BCE, derivative is to be calculated. So this step is about binary cross entropy loss derivative for the given input and output. So how to calculate the derivative? This concept was discussed, I am not repeating it. So formula is provided to you. If you forgot about it, revise the concepts which were covered in the very beginning first 2 weeks of sessions DL. Well explained and well implemented by you guys also. Binary cross entropy loss derivative. Loss with respect to the y predictions is to be calculated. Using this formula which is provided here, you can see here, y predictions minus y true values divided by y predictions multiplied with 1 minus y predictions. This is a formula. This formula you can implement in different forms also. You can use the basic notation of the implementation of this formula. So thus you can complete this part, 10A. Everyone who are sitting here need to complete these tasks. All these assignment needs to submitted in first 30-40 minutes of time. For the last exercise and assignment, these all exercises are going to be closed. Raise up the hands. Anybody completed this part? It's a two-step only. Each of these graded exercises are provided with the sample usage of these exercises, the codes which we are defining along with the defined test cases as well. All are individual gradings. Raise up the hands who are trying this part, BCE laws. Okay, it's not that difficult. Only two functions you need to define. Loss will be calculated between actual and predicted outputs. Y is our output parameter. So for the given Y true and Y prediction, actual and predicted values, we are computing the binary cross entropy loss using this formula. The loss between Y predicted and Y true is the negative of. Definition is given to you, formula is given to you, and the required torch functions which helps you to implement that. For calculating the log value, torch.log is there. For calculating the average, torch.mean is also there. Anybody done this part? Done? Okay. As an example implementation, two tensor were given to you, Y true and Y predicted. These are the true values and predicted values. Looking at the values of these tensor itself, you can find there is a difference between. But how much that difference is, that we are calculating using the formula of the BCE laws that we just defined. Once you define, call the method BCE cross entropy by passing these tensors Y true, Y and Y prediction, so that you will get the value is the loss. Loss dot item will give you the value because it is the data structure. Similar whether you can calculate the binary cross entropy loss derivative as well. When true and predicted values, you will get the derivative also. Okay, moving to the next part, 10b, implementing the fully connected layer, dense layer. Just recollect the network architecture that you studied in the very beginning sessions. Input nodes, inputs connected with a number of hidden nodes, right? Fully connected network with the dense layer. Input nodes will get connected with the number of hidden nodes in the network architecture. So with this association, you will have the associated weights and biases. Correct? Two things will be there, weights and biases. Dimensions of the weight and biases. If there are n number of inputs with m hidden nodes in the network, what is the dimension and shape of the weight matrix? N nodes in the input, n number of inputs, and m hidden nodes. What is the shape of the weight matrix? M by n. How many biases will you get? There are m hidden nodes. How many biases? M biases. Good. So, we are defining the class dense with the constructor method, which takes the input size and output size. N is the input number of nodes, output size is the number of nodes in the hidden layer. Number of input features and number of output features. With the given input size and output size, initialize the dense layer in the constructor itself. The parameters also I define myself. self dot weights and self dot biases. Both the size of the input and output is given to you for the dense layer. Now you have to define these weights and biases. What is the shape of this weight and bias is also provided to you. In the instructions itself, this is given to you. As I said, n is the number of inputs and m is the number of hidden units. Then obviously you would get the weight matrix m by n and m number of biases, one per each of the hidden unit. So the bias dimension would be output size by 1 unit for each of the output number of units, nothing but the hidden nodes. So two parameters, one is the weights and the biases. So initialize the weights and biases, then perform the forward pass. Okay, what will happen in a dense layer network during the forward pass? Given input, weights and biases, you have the things. Inputs you are having with you, associated weights you are having, input to hidden unit, associated weights you are having, and the corresponding bias, one per each of the hidden node you are having with you. What will you calculate during the forward pass, moving from left to right of the network? What happens? Linear function z equal to f of x plus, I mean to say elaborating, wixi plus b bias. Just do that operation. Xi is your input, W is your output, weights associated from the hidden nodes to the inputs, and you have the biases also. So linear function is z equal to wixi plus bi. Multiplication of the inputs with the weights and with added bias, it has to be written. This is the what is going to be written by the forward pass of a dense layer. Just implement it. Given input, and you already have the defined the weights and biases. So it has to return the output tensor after the linear, which is the result of a linear transformation between the inputs, weights and biases. Correct? So that is what forward pass of a dense layer. So coming to the backward pass, is it clear about the forward pass of dense layer? In the constructor itself, we need to initialize the weights and biases from the random distribution of the dimension is given, and in the forward pass, linear function is to be applied, linear transformation with the inputs and the weight with the associated biases. The formula is z equal to wixi plus bi. That is the tensor going to be returned by the forward pass. Now coming to the backward operation with the given output gradient and the learning rate. On receiving the gradients from the previous layer, now what you are going to do? You are going to update the weights and biases with the help of learning rate and also the gradients. So you have to calculate the input gradient and update the parameters. So calculate the weight gradients and input gradient and update the parameters. Calculate the input gradient and weight gradients. Weight gradients. Weights is the matrix with the dimensions what? Output size and input size. When you are back propagating and calculating the weight gradients, again matrix multiplication between with the input as it is. How? This also you already implemented. Dense layer implementation with forward and back propagation during the DL sessions. Calculating the weight gradient for the dense layer. So first of all, initialize the weights and biases from the random distribution with the dimensions which is provided here. Weight matrix is of shape output size and input size, and bias vector is of shape output size and 1, because one element for each of the hidden node, nothing but the output node or output size dimension. Once these weights and biases are initialized, the constructor part will over. Now let's come to the forward pass of the dense layer. What will happen in the forward pass of the dense layer? With the given input matrix, with the associated weight matrix and the biases defined, now we have all. Input is going to be provided to you with the bias and the weights which already we defined from the random normal distribution. Now you have to apply the linear transformation. Linear transformation Wx plus B. Weight matrix need to be multiplied with the input and bias will be added. That's it. That resultant is need to be returned. Once that part is over, let's come to the backward propagation with the output gradient received from the previous layer in the back propagation, moving from right to left of the network and with the help of learning rate. What will happen in the back propagation? Upon receiving the output gradient from the previous layer, next output gradient is to be calculated, which is to be back propagated back. Along with that, the parameters, both the weights and biases, need to be updated with the help of output gradient and learning rate. So what is this output gradient? Output gradient of the loss with respect to the so that you will get the input gradient, that is the gradient of loss with respect to the input x, which is to be returned. Return input gradient. Remember the consistency of writing the code. We are defining each layer, implementing each layer with the two methods, forward and backward. Same is the methods to be called up. And during the back propagation, whatever the network is input for the back propagation, we are calling it as the output gradient, nothing but the output received from the previous layer. What is calculated at that particular layer and which will be back propagated is going to be returned as the input gradient for the next layer. So the input for the back propagation is named output gradient and output is going to be named input gradient for the next layer. Anybody completed? Able to complete this dense layer? Once I complete the explanation, I can come to you so that I can help you. Okay, which part you are doing and stacking? Where you need my help? Part A is BCE loss. Second is the dense layer. Can you confirm how many of you completed here BCE? BCE loss? Done? Done? Good. Implementation of sigmoid activation function with the forward and backward methods. The definition of this sigmoid activation function and its derivative. You know, have you done? Good. It's a simple part. Right, next one, reshape layer. Am I correct? Yes. Move on to the last part, reshape layer. I told you very clearly what is the need of this reshape layer in the convolution neural networks. The dimension of the feature maps that has been generated after the convolution layer are multi-dimensions. These feature maps then will be given to the feed-forward neural networks, dense layers, in order to do these linear transformations. So while passing the output from these convolution layers or the max pooling layers, which are of multi-dimensional, to the fully connected layer or dense layer, which needs a input in one-dimensional representation, mapping is required, dimensionality mapping. That's what we are doing, flattening the feature maps of the convolution layers in order to get connected to the dense layer. Flatten layers in TensorFlow. So here the job is, reshape is the layer that we are defining. The job of the reshape layer is, given one input shape, it has to convert into the given output shape. So you just recollect the example which is given in the image of the convolution layer itself. At last, what you have calculated. Look at the image which is provided so that it will be easy for you to understand what is to be done. Okay, looking at this image, at last we are having 6 by 6 by 8. This is the output of the feature map that is obtained by a series of convolution layers followed by the max pooling layers. Now 6 by 6 by 8, this is the dimension 6 by 6 by 8 need to be converted into the 1D tensor. Nothing but a dense layer with the input dimension 6 multiplied 8. 6 into 6 into 8 number of neurons it is to be converted. This is the input size for the dense layer. Output size nothing but the number of hidden layers up to your choice, n number. So look at how this sigmoid activation is so simple and implementation of reshape layer. Look at how what are the instructions given to you. Create the reshape class and initialize the two parameters. One is the input shape shape of the input tensor. Second is the output shape, shape of the output tensor. Once initialization is done, then move on to the forward method, which reshapes the input tensor to the desired output shape. For that, you can use the function view. Torch.view will help you to do that job. Look at here, input is given, input shape is given, output shape is given. So, in the forward pass here itself, what is to be done? Input need to be converted into the output shape. That has to be written. Coming to the backward pass, on giving the output gradient and learning rate, reshape the output gradient back to the original input shape. Same is the job, same thing is to be done, but with respect to output gradient, which is reduced from the previous layer. To which shape? Input shape. So, you just written the reshaped gradients. No parameter updation, no learning. But as I said, for consistency, we are defining the signature of these methods are defining along with the learning rate parameter. Don't bother about output gradient and learning rate parameter, so that it will be easy for us to use the same method name backward. Whether you are using or not, don't bother. But here in this, no need of this learnable. There is nothing is when the parameter updation is not there. Over. Have you completed this exercise totally? Okay, let me see how many submissions are there from this. Assignment 10. 75, 75, 70. I hope you guys are failing with this test cases, right? Could you please confirm? 75 you are getting. Netaji Reddy and Pooja, Nandini, Samskruti. Which test case you are failing? You guys are getting 75 out of 100. Let me know which test case you are failing. First one, BCE loss. Where you are getting that error message? So, team member Mr. Pranay forgot to keep that message, passed all test cases, but it's a message only for getting confirmation. So, you guys tell me in which part of the code you are getting, I mean the sample usage code, which of these ABC parts you are getting that error message? BCE only, right. Maybe the reason why all of you got 75, 75, 75. Okay, anyhow we identified that one of the test case is causing the problem, leave it. 75 grading will be considered, but here it is not showing. No problem. We understood what is the issue is, but I can't do anything right now. Leave that part and let me check other activities. So, among all those 10 steps of building and training the convolution neural networks, all the implementation whichever are required for building the CNN is done. Now, the network architecture is to be defined and then model is to be trained on the sample dataset. That is the leftover part. In order to do this, all these remaining 8 steps need to be completed. Now, I will give you 10 minutes of time exactly, 5 to 10 minutes only, because we need to finish up that also. To complete earlier exercises 8, 9, 8 and 9, only 5 minutes. After 5 minutes, all these 8, 9, 10 will be closed and will be 11th exercise will be revealed. Hope I am clear. So we'll count the submissions till 5 minutes only. So 8 is about implementation of this convolution layer. Now will you come convolution layer, who is struggling and where is the problem? You able to get? Done. Implementation of convolution layer, implementation of max pooling layer with forward and back propagation, which we did in the last session 8 and 9, and today's session 10 with the remaining layers, reshape layer, activation layers and the supporting helper functions and loss function and derivatives. All these parts were over. Now the time is 5:10. By 5:15 I will close all these 3 assignments, we will launch the new assignment. Okay, 2 more gradings from assignment 8 and look at the assignment 9. Let me have a look on max pooling implementation. Yes, 10 submissions increased, max pooling layer. Okay, whomever are able to submit successfully, just recollect what you did. It's a lengthy process happening since week together. A month ago we started this discussion, convolutional neural network with image data, with an intention of building a CNN model without using torch libraries. We started our journey with building your layers by yourself, right? You defined your own convolution 2D layer, you defined your own max pooling layer, you defined your own reshape layer, how it will perform back propagation and forward backward propagations, each and everything. You defined your own what else, activation function. One of the activation function only we chosen, that is the sigmoid only for simplicity. Same way you have to build another whatever the activation function that you, probably we know very well that ReLU will be used at the hidden layers, but we restricted it to the simple CNN model with a single activation function, that's it. Okay, all these parts were done. Shall we move? Okay, I am going to evaluate last time. If you want me to wait for few seconds, I can do, otherwise I can proceed. No new submissions in assignment 9, nothing but the max pooling layer. Okay, 53 gradings. Yeah, 8 means convolutional layer, and I am checking now 10th one. So 75 grading, anyhow here I am going to get 0 gradings, fine. But 75 out of 75 score also fine. Okay, as I said, it's now 5:15. I'm stopping this. Okay, I'm closing 8 and 9. 8 is being stopped. Now let me move to the assignment 9. Closing the max pooling layer implementation. Anybody at the last stage of submission? No, fine. So assignment 9. Unreleased, done. Now moving to the 10th one, assignment 10. Okay, I'm closing. Done. Let's move to the next one, the last one. PSEL CNN assignment 11, which is released successfully. Could someone confirm it? PSEL CNN assignment level. Okay, come to this part. So provided with all the code to you. Now you can check whatever the mistakes that you have done. Let's move to the last part. Come to the last one. Assignment 11, implementing the training loop for the neural network. Come to the last part. Okay, just recollect. What is the meaning of training a network? First of all, network is to be defined. Okay, how many convolution layers? What is the shape and input for the convolution layers? And then pooling layers, and then what is the order, whatever the layers that you have defined. That network architecture is to be defined. Once the network is defined, then for a sample of input-output pair, this network is to be trained. What is the meaning of training? Performing the forward pass from left to right for each of the layer defined in the network, correct? Starting with the first input to the first layer, performing that particular layer operation, forward operation. If it is the convolution layer, perform the convolution operation. If it is max pooling, will perform the pooling. Whatever the layer is accordingly, right? So performing the forward pass from left to right, starting from the first layer with the input given to the first layer. The output produced at the first layer will be the input for the next layer. It's in a sequential order. This has to be continued for all the layers which you defined in the network. This is forward operation. Once this is calculated, you will get the final output of the network. With this output, already you have your required output. This is obtained output, predicted output. Your true value is also there with you, with the training data set, right? These two will be compared and the loss will be calculated. You have defined a loss function for your task. What is that? BCE. Once the forward operation is done, for each layer of the network, compute the loss. With that loss, now you need to do the back propagation. What is the very first step in the back propagation with the loss? Loss gradient. Once you got the loss for all the output which is obtained from the forward pass, calculate the loss gradient. You have defined the loss gradient. What is the loss? BCE. BCE gradient also you divide. BCE derivative between the output, actual output and predicted output. This gradient has to be back propagated through the network to the other layers from right to left. What is the meaning? Before this is prior to this one, during the forward propagation from left to right. During the back propagation from right to left, you need to loop over each layer of the network, starting with the loss gradient calculated at first and moving that back at each layer. Recollect, we have defined a parameter input gradient. Upon receiving the output gradient, every back propagation definition of all the layers. That has to be back propagated to the first step along with the parameter addition at that particular layer if it is eligible. Got it? That you have to do it right now. So look at this exercise. Just come down, scroll down a little bit. This is the simple network configuration which is given to you. Very basic network configuration. Will you have a look on? This convolutional is the layer which we have implemented. Our convolutional layer is convolutional, not conv 2D, which is of NN module. Clear? Okay. 1 by 5 by 5, the meaning a grayscale image of height and width 5 and 5. What is this 3? Filter size, convolution operation you are performing, size of the filter 3 by 3. And what is this 3? Number of output features, channels, output channels. Look at how convolution was defined. Scroll up and just have a look at how convolution, what are the input parameters for convolution operation. Where is that? Okay. Input shape, that is 1 5 by 5, kernel size 3, and the depth, number of channels, again 3. Some number of channels, filters, how many output features you want. You just have to recollect all the codes which are there, which is provided to you, right. This is the dimension which is given. This is the convolution. This how I defined my first convolutional layer. I said repeatedly, I am saying layer means along with the forward. Convolution layer along with this. So followed by the next is the activation function, sigmoid, which we define. Right. Next is the max pooling layer. How I define? Max pool 2D MP 2D capital. This is how we defined. Not the NN module max pool 2D, remember. So how the max pool 2D is defined? What is this first 2 by 2? Pooling window size, and this 2 by 2 is striding. Okay. Then very simple, I said, one convolution, one max pooling, and then reshaping to mapping it to the fully connected dense layer. My dense layer is dense itself, right. So what is the shape which I defined? Actually here is, that's what I am saying repeatedly. So my input is 1 by 5 by grayscale image of what is this 3? Number of output features, am I correct? So when you apply a max pooling operation, with this input of 5 by 5 and 3 by 3 filter, what is the resultant output image? 5 minus 3 plus 1, right? So what is the image shape? 3 by 3. After this convolution operation, 3 by 3. Am I clear? On this 3 by 3, what we are applying? Max pooling of 2 by 2 with 2 by 2 stride. So what is the output? It's a scalar value. 3 by 3 image and max pooling with 2 by 2 window with stride is 2 by 2. What happens with the max pooling? Max pooling size by stride. 3 by 2, you will get one scalar value you are getting. So this reshape is to be defined in such a way, which is to be adjusted in a proper way. So I am getting the output is, my output is a scalar value. So what I am doing, this output, what I am getting the scalar value 1 by 1 is mapping into the one dimensional vector. So that the next layer I am connecting the dense layer which is taking is, this outcome is 1 with the number of hidden nodes. This is your choice, 50 or 100 or whatever the number you want, hidden nodes only. Dense layer followed by the sigmoid, I defined only one activation function, sigmoid, followed by one more dense layer which is giving the output 1 with the sigmoid. I am doing a classification, binary classification with the sigmoid activation. So if I run, okay, this is how my network is designed. Once this network is designed, now I defined my extrain data with the torch random of what is the shape? This is the shape we defined, the input shape. So one batch size, first dimension is the batch, of the image size is grayscale 5 by 5, what we defined in the input shape of the network. and white, this is my X train. Okay, and what is my Y train? Only one value it is returning, torch tensor of dimension. Possible value is the actual value is 1, labeled 1. So that train is called up with the network binary loss function along with this, by passing the X train and Y train and ran for number of FOs. So this is how this network was used. Okay. Leaving this part, just have a look on this network, how this network is defined. That's fine. Now move aside, so, a step up, come to this part. Now we are at the stage of implementing this training loop. Coming to the implementation of training loop, how I define this into two functions. One is the predict function, second is the training loop. So I said during the forward pass from left to right, with each layer of the network, forward operation is to be done with the input passed to the very first layer. So that for that performing this task, we defined a simple function called predict. Given the network and the input, it has to return the final output of the entire network after passing all the layers of the CNN network that you define, and implement this one. Do this. So this part you have to. Is it clear this part? Predict is the function. So we hadn't yet entered into the training phase. During the training phase, forward propagation has to be done for each layer of the network. That we are defining in a separate function called the predict. Given the network and given the input, what this predict will do? Perform the forward process of each layer from left to right across the network. I am giving you the clue also. Forward pass of each layer. That's the reason why I am telling from the beginning. Each layer has been implemented with the two methods. One is the forward, second is the backward. Same is the type signature we used for those two methods. So what is to be done in the predict? For each layer in the network, just call the forward method by passing what is the parameter for forward method? What is the parameter for forward method? For the first layer, input itself is the parameter. You can say what is the signature parameters are there in the method. Network comma input. Input is given. But input will be the input for the first layer only. Remember that. It should not be the input for the rest of the layers. It's going in a sequential manner. This input will be the input, should be the input for only the first layer of the network. So output of the first layer will become the input for the next layer. That you need to implement. Have you done it? Done. Done? Okay, let's move to the next part. So coming to the training part. Given the network with the given loss function BCE loss and its derivative BCE derivative and the X train and Y train we have taken, we have seen how it was defined. Sample data set for a number of epochs with the learning rate, we are defining the training block. Now what is the meaning of training? We already defined how to calculate for each layer. With the input, how to calculate the output of each layer is done with the predict method. Good. So for each of the epoch across all the epochs, we want to calculate the error with each epoch. So we initialize the variable error variable. For each of the pair of input output, from the X train, Y train. All this part was discussed in the DL sessions itself. These steps were discussed in the DL sessions itself. Right? For each of the above, for each pair of input output X and Y from the X train, Y train, now write down the code here. Input is there with you, X train, and actual output is also there, Y train. Now with the given input X train, calculate the output. How to calculate the input with the given? You already defined the function just prior, that is predict. So pass this input X train to the predict method, which will give the output. Now that output with the actual output Y train, calculate the loss. Predict is the method which is defined, which will calculate the final output of the entire network. In such a way you have defined. So the output will be passing this input, nothing but, what is the input here? XY is the pair. For each sample input output pair XY from the X train, Y train, so your input is X. Your actual output is Y. From the input X, you have to calculate the network output using the predict method. In such a way, you have to define this predict method, which will compute the final output by performing the forward pass of all the layers. Done. So once you calculated the output, what is the next step? Loss. Error is to be calculated. Done. Once error should be cumulative across the samples. Once done, what is the next step? Loss gradient. You have the loss derivative which is passed through the network. Binary cross entropy derivative is the derivative function which is defined with loss underscore derivative variable. So calculate the loss derivative. Done. Okay, for the obtained output and well, this one, actual output. What is the next step? So what you are getting with calculating derivative is nothing but the first gradient. Now this gradient has to be back propagated through all the layers from right to left. What is the meaning of back propagation? Yes, backward method of the layer is to be called up with the network, considering the network in the reverse order. How will you ensure back propagation from right to left? You have to ensure the movement from right to left. For each of the layer in the network in the reverse order, call the backward method. Done? Okay. Over. So this part will over by writing all this part of the code, whatever we discussed in this level, and you are calculating the error across the each epo out of this for loop. Then you are displaying. If you are able to complete this part of the code, run the code cell, entire code you can run all, and run the network configuration and train the model and see the output. Anybody getting the output? Did you observe the loss, decay in the loss value? Reduction in the loss value for 4 epos. We are training this network for 4 epos loss value. Okay. So hope you understand. Okay, how many have got executed till now? 2 members. One training part completed. This is how you have to build a convolution neural network. A very basic simple CNN model we built. Even if you try with somewhere different architecture, obviously you will get failed. Let me try with it. Sorry, if I have the code solution only, na? Okay. Try with the 3 by 3 image. Sorry, color image. Here is a grayscale image we have taken, right? Huh? It's not executing. What is the error you are getting? Probably you might get the errors because of max pooling layer, I think so. Not editable. Okay, create one more network architecture in the next cell. Yeah, we made this is uneditable. Okay, because of valid test cases are there. Take another code cell and define another architecture and make it as a color image 3 by 5 by 5 and leaving the remaining, okay, 3 is the kernel size and something errors you are getting. Probably that might be because of max pool. Okay, do one thing. Comment the max pooling layer or remove the max pool layer. Use the convolutional layer. How you define the convolution? 3, 5, 5, right? And filter size, kernel size is 3, right? Number of channels? 3, na? Okay, done. Okay. Okay, do one thing. First one thing, do one thing. Leave the grayscale image only, 155, and just remove the max pool layer. So what will be the shape you are getting out of this convolution operation? Don't use the max pool. Just convolution 1555 with the filter size 3 and 3 output channels. You will get the dimension, just recalculate. Number of output features is 3. So 3 by 5 minus 3 plus 1, meaning that 3 by 3. So 3 by 3 by 3 you will get. I am just writing it here, but I can't use this. This, okay, we'll do one thing. Okay, 5 by 3. So remove, as I said, remove this max pooling layer. Okay. So the dimension I would get is 3 output features, each of size 3 by 3, correct? With the convolution operation. Okay. Now this has to be reshaped to all these three things to be multiplied, right? Into 3 by 1. So that 3 by 3 by 3 into 3 means 27. So now I need to the dense layer with this dimension. So input units to the dense layer will be 3 into 3 into 3 and the number of dense nodes, hidden nodes is optional. Okay, can you run this network? So reshape is to be adjusted according, readjusted. It should be readjusted according to your image that you are passing. Done? Okay, thank you. So the problem is with the max pooling layer. It's not the problem that max pooling was implemented to very base case. Same output. Error. Okay. 3 by 3 correct. 3 by 3 image we will get 3 into 3 into 3 multiplied. So anyhow the concept is we have to adjust, readjust this reshape layer according to the dimensions that we are getting. So, if we do the modifications in the max pooling layer accordingly, which can handle the number of batches of data, we could be able to successfully run. This one, dense layer. No, this is the last dense layer. Last dense layer is one node which will produce either of the output, sigmoid activation, for my binary classification. This here you can define number of layers also, that is not the problem. So, it will generate number of outputs. Okay, right. So, with the given configuration, were you able to submit this? Do the submission. Leave this part is experimentation. With the given configuration of the network, how many submissions are you able to do? So, let us finish off this part. 5 minutes time we can finish. Any submissions from your end? Only 3 to 4 lines of code only. Working? Fine. What is that second architecture? Okay. What the correction you made? Fine. So, do the submissions. Once you done successfully, so probably with the different network architecture, you will get dimensions variations according to the pooling operation adjustments to be done and reshaping layer to be used in it. Sorry? What you are saying? Second architecture. Okay, you do that. So, define the predict method and define the steps in the training loop. This will over. Still any doubts regarding these two?